We are given a flow field, and we want to determine whether it is rotational or irrotational. We're given a velocity vector in cylindrical coordinates with an r component of 0, a theta component of c, some constant, times r, and a z component of 0. Now, what we should first start out by noting is that if our vorticity, denoted by zeta, is equal to curl of our velocity vector, if that is equal to 0, then our flow is irrotational. And the reason for this is, you can imagine if we have some sort of rotating flow here and some sort of vorticity, we're going to have a vector essentially spanning across that center. And that's going to be our vorticity, or our zeta here. So if that's equal to 0, then we essentially have no vector, or we have no vorticity forming. So now, on the opposite case, we can say that if our vorticity, which again, equal to the curl of our velocity vector, if that is not equal to 0, then we have rotation, or it's rotational flow. Because in this case, we have some sort of vector, and we have flow that's rotating about it. So now, what we can start out by doing is calculating our vorticity to determine if our flow is rotational or irrotational. So, I mentioned before that we're in the cylindrical coordinates, so we're going to have to follow the rule system for our matrices. So we're going to start out with 1 over r times e sub r, and then we'll have r e sub r, and then e sub z. Oh, sorry, this is e sub theta. And then we'll have our partials coming from our gradient. So we'll have partial r, we will have partial theta, and then we will have our partial z. And then for our velocity, so we'll have 0, we'll have c sub r, and then 0. But again, we're following the rules of our cylindrical coordinates, so we actually have to multiply this specific component by another factor of r. So now, we can start to evaluate this. So we'll have 1 over r, and then we'll have e sub r, and then 0 minus our partial z times cr, which that's essentially just going to be 0 because we have no z in our cr. And then we'll have minus e theta, and then this will just be 0 because we have 0 times 0. And then we'll have our e sub z, but for this, we'll have partial of r times cr squared. So what we'll get from this is 0 er hat plus 0 e theta hat plus 2c ez hat. So in this case, we can see that our velocity vector is finite and it is rotational. And we can say it's rotational because our vorticity, or zeta, is equal to, again, curl of our velocity vector, which is not equal to 0.